Today's topic is designing carbon filter systems. And this is a entry-level look at the factors you have to consider in designing carbon filters. In everything we do with carbon filtration especially, it's all based on sort of a column, a packed column idea of water flowing through a column of media and how long it takes to remove a specific contaminant. So that being said, we're going to take a look at carbon itself real quickly. And the effort to produce GAC. It takes, to make 1,000 metric tons of activated carbon, it takes 3,000 metric tons of carbonized coconut shells burned in, a pit without any oxygen. It takes 7,000 metric tons of raw shells to produce that 3,000 metric tons. And then 40 million coconuts to produce that 1 metric ton of activated carbon. And this is or 1,000 tons of activated carbon. And that's just a drop in the bucket of what the world consumes. That's a lot of coconuts going into our filter systems. But please note, just to let you know, it's that time of year. Due to COVID-19, there's been a labor shortage in the coconut groves around the world. And therefore, this cascades into an issue with getting carbon made out of coconut shell carbon. So if I was a gambling person, I would wage heavily on seeing an increase in price in coconut carbons out there in the marketplace. So it takes a lot of raw material to make GAC. And when you aren't getting it out of the tree and doing it quickly, price is going to go up. So understand that's coming at you in design of systems. But now let's take a look at that natural product that we're talking about, because activated carbon is made from any carbonaceous source. So we're going to talk about different factors that influence the performance of activated carbon and how do we sort those details, right? You have micropores, mesopores, and macropores. Small, medium, and large pores in activated carbon. These do different removal processes in activated carbon because we're talking less than 20 angstroms in the micropores, less than 500. An angstrom is 1/10,000,000th of a millimeter. That's incredibly tiny. So you're literally talking molecular scale here about things going on in size of pores that things can fit in. So activated carbon on a whole, volumetrically, can remove 0.1 pounds or 45 milliliters of a contaminant per pound of GAC for absorption. Just a general guideline, right? Well, that's an interesting concept. Different things are removed better. General rule of thumb. But mesh size, this is something that's always kind of a bit puzzling. What's 80 by 30 or 80-30 mesh size? Well, these are fractions of an inch. This is 1/8 of an inch size grains to 1/30th of an inch size grains. This is 1/12th of an inch to 1/40th of an inch. This is 1/20th of an inch to 1/50th of an inch size granules. So the larger the numbers in the mesh size, the finer the grain size is. And larger mesh equals better flow. Smaller mesh equals better removal. We're going to be balancing those factors when considering a design of a system. Iodine number is a relative surface area. For water treatment, we want an activated carbon between 900 and 1050 on the iodine number. Now, an abrasion number is how hard that GAC is. This is important for designing backwashable filters. Why? Because we're going to be tumbling that activated carbon around. It's going to be smashing off each other. We don't want an activated carbon that's going to crumble and then get backwashed out because we're losing our media, right? For water treatment, we want to have that greater than or equal to 70 for that number. And the CTC, This is a number used in vapor phase, but also in liquid phase for small organics. This is the number you're going to associate with your trihalomethanes and things like that from the water supply. Now, tannin number is the dose of carbon to reduce the tannin amount by 90%. The smaller this number, the better. You're going to get these numbers from your carbon OEM. Remember that. Trace capacities measures the micropores for removing small organics. So if you're dealing with designing a system for trihalomethanes or some really small volatile organics, you're going to look at this trace capacity to augment your design. So know the media you're using and carbon you're using. There are an immense number of varieties of activated carbons on the market. And between standard activated carbon and catalytic carbon, there is a wealth of other products on the market. So how to understand what your activated carbon will do and what it will remove, that comes down to isotherms. Isotherms are a great place to start, especially if you're dealing with a contaminant in a water supply where it's important to the end product water, okay, where we need to remove a specific contaminant to ensure we do not have failure, okay? And that's the interesting thing about activated carbon. We can predict how well it will remove an individual contaminant, but we have a really, really hard time in a mixed contaminant scenario predicting how all those things will be removed. Why? Because selectivity, that same idea from ion exchange about how we can, resins will prefer one ion over others based on size and charge. Pretty simple to understand there, right? And we have a limited number of ions we have to deal with ion exchange. Well, in activated carbon, we're dealing with everything organic. And as an organic chemist, this is a number that is incredibly large to have to understand the selectivity of all those things. So generally, we're doing it in categories or families types of compounds rather than individual ones, because it's really, really hard to determine which is going to be more selective for others. But if you want to look at a specific contaminant, go to your carbon OEMs. They have these microtherms in their files. Why? This is what they do day in and day out. And after some rather long time searching these out, it's difficult to find these in literature. Why? Because most of the work is done by private companies here on these things. The stuff in literature, very, very difficult to ascertain or discover for useful product sizing sort of information. Leverage your carbon manufacturers, not necessarily your distributor. You want to talk to your carbon manufacturer. They'll also help you design a system too. So how does carbon remove contaminants? We always talk about adsorption as a general topic. Well, that's broken up into two categories, really. Physiosorption and chemisorbtion. Okay, physiosorption is a reversible process that just coats the carbon and stuff can be backwashed off or washed off. And this is for smaller pores of the carbon, larger pores of the carbon. For wood-based, we can actually backwash some of this. Some of this we can treat and wash off. Designing the backwash system may help remove some of the stuff and help regenerate activated carbon partially. But a lot of things depend upon the contaminants properties as well, whether or not you'll be able to make this reversible. Then there's the chemisorption process. And this is where we're catalytically changing a contaminant into something that's not an issue, or we're physically bonding it to a carbon, activated carbon, in a way where it's irreversible. It's trapped on the media. So this depends on the number of activated sites on the carbon and the availability of those sites as well in the column that we've designed this system around. So you typically have impregnated carbons for this process, but there's spots out there. This is why you can get activated carbons that are specific to nitrates, specific to tannins, specific to lead. There's a lot of designer products here. So it's worthwhile, if you've got an interesting challenge, reach out to your carbon manufacturer you're buying from. They probably have a product that does a specific contaminant a lot better than the general stuff you're using for all around purpose work. So understand that those options are out there. So there's really three processes here with one media. So activated carbon is this amazing stuff we've been essentially using since the dawn of civilization to do our purification work. Now, the chemoabsorption of chlorine and chloramine follows a couple different paths. So we're going to go through this rather quickly. We're converting chlorine to basically hydrochloric acid below a pH of 8, but it's such a small amount, it doesn't affect overall water chemistry at all, nor is it harmful to you. If at above a pH of 8, we no longer have that proton because it's been used to buffer the pH of the water, you just get chloride ion out. This happens incredibly quickly. Do this very fast. Now, chloramine removal happens via all three of these pathways, and these are much slower than these two. Incredibly slower, orders of magnitude slower. Okay, so understanding selecting the right carbon here is critical to doing this well. And you can see here, if you get some high levels of activated of chloramine in a system, you can produce quite a bit of acid out of it as well. So there may be some chemistry impacts as well here. I've heard of systems shocking with chloramine well above 10 parts per million on times of municipalities that they don't inform us of. And this is what's going to result out of it, is these sort of reactions. And some of it is straight gassing off of nitrogen. Others were producing ammonia, which would be absorbed into the carbon as well. It's much harder to remove chloramine from water than chlorine. Now, you have to understand the characteristics of the individual carbon you're using. Understand it, know it, it's part of your toolbox. Particle size, activity, pore structure, physical properties such as hardness dictate your selection of choosing product. There's not one single product that is the best option for every carbon application. So in general, coconut shell-based carbons are used for low concentrations, small volatile organics, where the hardness of the coconut shell is an advantage. Coal-based carbons are the jack of all trades and masters of none. So it's a real general use, used a lot in municipal work. Wood-based carbons are generally used for decolorization applications because they tend to make larger pore mesopore sizes rather than micropores. So really, really interesting uses of selection of carbon. You may even wish to blend all three in a design depending upon applications and in multiple meshes. You could put your larger mesh on the bottom and your tinier mesh on top and get stratification of purification going on as well. All carbon is not the same. So we've talked about the attributes of carbon itself. Now it's time to do some math. Unfortunately, it's math time. One of the first things we need to understand when we are talking about carbon filtration, especially in relation to Fleck and autotroll valve in structural tanks, is tank size. We have to start with that surface area. That acts as our initial contact plane of water meeting carbon. And then it's the column that we're defining below that. For most applications of activated carbon, we're going to have a 30 to 36 inch carbon bed, period. It can get bigger, longer than that, but typically it's not shorter than that. But we also need to understand the surface area as well, because you can get a thinner bed when you have a wider surface versus a taller, thinner column. And what's going to work best for extraction? That all depends upon your application. So the quick factor for doing this is in inches. Square foot area is 0.005454 times the diameter of the tank squared. Okay, so that's the diameter of the tank squared times this factor equals the square feet of the tank bed. This defines your filter count. Okay, so in a 10-inch tank, 10 inches, 100 inches squared times this number, it works out to be 0.55 square feet of tank bed area. This lets us know what surface area that water's got to transition through in order to get through the tank. The reason we're doing this is because this is a number we need to plug into formulas for empty bed contact time. Now, empty bed contact time is what this is all about. Those isotherms that predict what we can do are all based on empty bed contact time. This is taking raw virgin activated carbon, putting a certain amount of contaminant in a beaker full of this stuff and measuring how long it takes for that carbon to adsorb, chemisorb, physiasorb, whatever process it takes that carbon to remove it. And that equals the bed volume in cubic feet times 7.48 gallons per cubic foot. That's a water conversion here, times the flow rate in gallons per minute. Okay, so this way, if we have empty bed contact time for a contaminant, if we have this variable, the flow rate that we need by our customer, we can solve for the bed volume. If we have a specific bed volume already, we can determine the flow rate in a single pass that will remove 99.9% of that contaminant because we have those numbers. So basically what we're trying to do is get you the point. We're going to design around empty bed contact time. It gets us the result we need in a single pass. That doesn't preclude progressive flows with smaller tanks at higher velocities where we're doing a 50% reduction, then another 50, and then another 50. You can design that way as well. We're just taking a look at single pass design systems today. And you're going to do that from the isotherms. This is loading in milligrams per liter versus residual concentration. So it lets us know at what concentration, how well we can load that carbon. And will it be able to achieve our results? So this tells us how to characterize our carbon for what it does well. And this is what your carbon manufacturer has in their files. So how to use that empty bed contact time formula? Well, empty bed contact time is the time it takes to absorb or chemisorb a specific contaminant with a specific amount of GAC. It's all based on real world lab data. And this is based upon the flow rate per square foot of filter bed area. Okay, so here's some rules of thumb for an appropriate carbon media. For free chlorine, it's 1 to 2 minutes. These are very conservative numbers, by the way, guys. This is in reality 30 seconds to 45 seconds at 10 to 15 GPM per foot squared. Chloramine, more than double the contact time at half the flow rate. This begins to tell you how hard it is to remove different things just by looking at the empty bed contact time. Organics, 5 to 6 minutes at 1 to 1.4 GPM. Toxic organics, 8 to 10 minutes at 0.7 to 0.9. This, they're just doubling this time frame or having the flow rate. PFAS, the contaminant du jour, falls in the same category as toxic organics at the similar flow rate. Different contaminants are removed at different rates by the same activated carbon. And they're going to be competing for space on the activated carbon. So this is probably going to get removed a lot quicker than this stuff. So how do you calculate the carbon bed volume you need if you know you have a customer's desired flow rate out of the system. Okay, I took free chlorine. Took that number, taking a slower worst case scenario of 2 beds, the slower design I could make here, 2 minutes. Plug it into the desired number. The customer wants 50 GPM. I'm just going to solve for my bed volume because these numbers go into each other. You end up with a 7.48 times the cubic bed volume. That's my variable in parentheses there. 50 times 2, because I multiplied each side by 50, times 2. So I get 100, this 100 equals 7.48 times the bed volume area. Well, 100 divided by 7.418 equals the bed volume. Well, at 2 minutes, I need 13.3 cubic feet of carbon. We're pushing the water through faster. At 1 minute of empty bed contact time with that carbon, I need 6.6 cubic feet of activated carbon. So you can design around those parameters on what you wish to use. So this is the type of thing that's going to determine how much carbon you need in a square foot in a tank to remove that. It needs to be a minimum of 36 inches or 30 to 36 inches. And then what diameter tank will make up my square footage. Now, if I wanted to do that same calculation for PFAS in a single pass system, same numbers, except I'm using 7 to 10. Okay, I'll use 7 for the first example. Same calculation, 50 GPM. Go through those simple calculations. 350 divided by 7.481. For 7 minutes of empty bed contact time, I need 46.79 cubic feet of carbon. And for the 10-minute empty bed contact time, I need 93.57 cubic feet of carbon to affect this removal. A lot slower than the activated chlorine scenario, and I'm going to need a very, very different vessel, many vessels to achieve this means. Now, let's say I only have a 1 cubic foot bed on site, and I want to know what I'm going to be removing with that carbon that's already on site if they ask me about a contaminant, right? So let's say we have a fixed volume of 1 cubic foot, but I don't know the flow rate I'm going to get reasonably out of that unit to remove all the chlorine out in one pass. Well, you may want to design a system that you don't necessarily want all the chlorine coming out. You're fine with a little bit coming through. That's what we're getting at here. So you do the calculation, you get a flow rate of 3.74 GPM out of the unit at 2 minutes of empty bed contact time. And you get 7.48 GPM out of a 1 minute empty bed contact time. Almost twice as fast, twice as much GPM going through the tank between the two. So a 1 cubic foot softener is going to give me up to 7.5 GPM without having any chlorine bleed through at all. That's nice to know. So that means an average house of, with 3 bathrooms, I can run every shower at once and not have any chlorine leaking through. Okay, this is going to be adequate for just about any home, to be honest with you. So how much will common designs remove? This is one way to look at it. If you wanted to say that same bed, well, we know how much chlorine we're going to remove, that's no problem. Well, what about PFAS? Well, I'll get rid of all the PFAS at a 7 minute empty bed contact time if I'm flowing only a gallon per minute. I will get rid of less than 100%, and I'll only be able to flow less than a gallon, 0.75 GPM at 10 minutes of empty bed contact time. That's a significant decrease in flow rate. I do know I will be removing some of it, but not all of it at those higher flow rates. This is going to tell me for PFAS, if I don't want to change the size of their system, I may want to sell them a reverse osmosis system instead to manage that issue. Just so it lets you know what you've got in the field, what it's actually doing for that contaminant, and do you need to modify it, or it will identify other opportunities to sell different treatment as well, especially if you have a customer that's concerned about that contaminant specifically. So other design factors, we got to take in mesh size into this as well. The reaction rate of a 12 by 40 mesh is twice that of an 8 by 30 mesh of the same product. So you can get twice as much reduction just by changing the mesh size. So the same exact activated carbon, just ground to a different mesh size, can give you better extraction. But it's also going to limit flow because you're creating a tighter packed column. So general purpose application should consider a 12 by 40 mesh. 8 by 30 is generally reserved for more commercial applications or industrial applications. And a 20 by 50, that's a really tight mesh for really particular customers. So for chlorine removal, an adequate filter design should have 4 to 10 GPM per square foot of surface flow with a peak of 12 to 15. Volumetric flows 1 GPM per cubic, 1 to 10 GPM per cubic foot. So you can handle up to 10 GPM per cubic foot of material in an activated carbon tank. The more media you have, the more flow you can have. So mesh size impacts flow and contact time significantly. So we've taken those factors into design. Well, one of the key things that we want to consider is backwashing that carbon, cleaning it. Why? Well, bed lift and expansion are important to every column design filtration method, okay? And backwash allows us to clean up that bed. To do it properly, we need 2 bed volumes of water going through the tank to clean it up. So in a cubic foot tank, you need 14 and a half gallons of water to go through at the proper rate to get a good backwash. Why? Well, this allows us to scrub that media together, help get those organics off the surface, get the dirt off the surface of the carbon. Why? If you've coated your carbon in dirt, it can't contact the water. It can't exchange anything. So clean carbon's a must if you wanted to remove anything from the water. So backwashing helps a lot prolong the life of a system. Plus, it will scrub some of that stuff off and get it out of the system as well. And then it's going to reorganize the bed. You know, you have that 8 by 30 mesh or 12 by 40. Well, the larger pieces are going to go to the bottom of the tank and the finer stuff goes to the top. And what did we just say about mesh size? The finer the mesh, the better removal. We want that at the top of our tank, not at the bottom of our tank. So backwashing reorganizes the tank so that the media performs better in a column as well. So always check your OEM's spec sheets for backwashing criteria, because this is going to be OEM specific. So double check that information. So for activated carbon, bed expansion is typically 20 to 40%. I shoot for 30%. Why? Because that'll balance out seasonal changes in temperature, because backwashing is temperature dependent. You're going to want to backwash for at least 5 minutes until the backwash water is clear, and the bed should be expanded a bare minimum of 20% to properly. So what are backwash rates for carbon? This you may have to contact your OEM to get this information, because it can be hard to find as well. This isn't on all their spec sheets, by the way. Got to do some digging. This is the same product in different mesh sizes. Here we take bed expansion at 30. I like to use the 15C number because that's about average. and I'm going to need a 30 meter per hour flow rate to get my bed to expand. For this mesh, same carbon, different mesh size, I need a 30.1 meter per hour flow rate for that carbon. So understanding the differences in mesh size will also save water and things like that as well, and improve performance in the same tank. And then you can see the difference in pressure loss here as well. Same water, you're going to get a pressure drop for that water based on granule size. Notice it's higher with the finer mesh than the larger granule stuff. Just tell by the scale and inclination of those lines. So, issues that arise when you don't backwash your carbon properly. Well, debris is coating the media, preventing function. You have a loss of capacity due to that following. Dirt load might break through to surface, come out dirty. Increased potential for biological growth in the tank. With activated carbon, depending on the bacteria, that may not be a bad thing. So we do use bacteria with activated carbon in special cases. We don't want the wild stuff though. Media bed compacts over time and compresses and resists flow. Pressure drop in surface water because of the filter cake built on top of the bed, and excessive wear and tear on the valve because we are backwashing. We're not getting all the dirt out. We're leaving grit behind inside the head. And then premature failures and leaks. So we're going to correct lots of different things to do that. Some of that's increasing backwash time. Sometimes it's just using a backwashing filter versus like an exchange tank scenario. And then water temperature and pressure impacts. And another thing that is optional for a backwashing filter, especially if you're concerned about organics or its specific application, warm water backwashes. We'll get into it in a moment. But there's other options for carbon. You can use exchange tanks with an in and out head. Okay, this is done a lot in industrial practices. Why? Because they're going to swap out tanks and basically they're going to be filtering in series at much higher flow rates and doing step down reduction. We're going to take out the first tank, slide a new one into the end of the list and move them all down. And essentially what they're doing is they're going to be sending this carbon back to be reactivated or regenerated at their manufacturer of that carbon. They're going to be reusing that. Okay, but upflow without a filtration valve can be done on these tanks. The pros, no cost of valve. There's no expansion of bed because you're going to be filling that entire tank with carbon. There's no freeboard there. You have lower water use because you're not backwashing. More carbon in the same tank. And the cons of that are dirt load. You're going to get a fouling at the bottom of the tank and a mud ball that's going to be difficult to get water flow through if you have a dirty water scenario. And the media must be monitored for failure or breakthrough. So you're going to either have someone sampling water here or specialized sensors to trigger that say, hey, stop using water. You need to change this tank. Okay. You can do this also with downflow in and out adapters. Same pros, no valve, no expansion in the bed, lower water use, more carbon in the same footprint. Same cons, dirt load falling at the top of the tank. Media must be monitored for failure and breakthrough. And these are quite often done in a lead lag scenario so that when one starts to fail, you have another one to pick up. And sometimes that's done in series flow where you're sizing it for a 50% reduction through each tank rather than a single pass system. That's how these are leveraged in a lot of ways, is for that. So let's say you've got a small, low-level area to get into and you can't get backwashing valves in or a large tank in. That's where series exchange tanks come into play. So understand that's out there as well. Other design factors to consider. Series flow for stepwise reduction. I just mentioned that. For higher flow rates than predicted by empty bed contact time. So I may be able to quadruple my flow through a tank by using 4 smaller tanks in series, than using 1 large tank and going through the column to get 100% removal. So understand you can design in stepwise reduction if large equipment size is cost prohibitive for you. Size the system for the contaminant you wish to remove. Don't size everything for chlorine. Why? Because chlorine is one of the easiest things to remove with activated carbon. If you're really looking to remove PFAS, size it for PFAS. It's going to take care of that chlorine, no problem. Toxic chemicals removed from water may require special disposal via the carbon OEM. So if you're removing something especially nasty, you can't just throw this stuff in the garbage as a commercial operation. There are programs, check with your carbon OEM, where you can send it back to them and have it recycled or high temperature incinerated and disposed of. For organic removal, you may want to consider a warm or hot water backwash that will partially regenerate the GAC. Why? Oils and water don't mix, and warm water helps force that oils off the grains as well during the backwash. So if you've got a treatment process where you're doing activated carbon, water softened, and a water heater, using some hot water to backwash your carbon filter with, if it's really geared towards organic removal, will partially regenerate that GAC and keep it fresh longer. You just have to make sure your valve and tank can handle that warm water backwash. That's a very special case scenario there too as well. So understand there's more options than just the regular in and out tanks with these things. So contact your carbon OEM for help and design. That's what they're there to do. They have all these isotherms on their individual contaminants for their individual carbons. Reach out to them. They're happy to help you design a system. And for the most part, our large carbon manufacturers are in water treatment as well, but they tend to deal with very, very large scale commercial operations like power plants. Okay, so what we're doing in the light commercial space or this smaller industrial space down to the residential space, we're the bonus cells for them, to be honest with you. But they're happy to help us design systems so that we use the right carbon for the right job in the right environment. They will help you design a system. Why? Because they still want to sell more carbon, and we move a lot more carbon than they think we do. And they get that. But you need to contact them, because if you ever go to these guys' websites and start looking at the different markets they serve, and then you pull up those each individual markets and you look at what products they have besides what you've been using or what your distributor may carry, you may find a solution for your client that you would have never discovered otherwise without talking to these people. So get them involved at the front end of your design, and they will help you design. Why? They're doing this work day in and day out, and you're selling their product for them. So leverage these people. Pentair, we're not a carbon manufacturer. We're a component manufacturer. We leverage them as well. We buy their products as well to package in our filters. That's where we're getting our information. You should too. Get it right from the guys who really know this material inside and out, day in, day out. So if you haven't explored the realm of activated carbon and treatment, today's discussion was a 5,000 foot view of it. Lots of complexity here, lots of creativity here, lots of choices here. So if you've got a problem in design or have a problematic issue, get your carbon OEM involved and they'll help you design around it, and we'll help you make sure you get the right tank and the right valve to do that job with it as well. So if you have any requests around training, anything structural, Pentec, Fleck, Autotrol, anything in the Pentair universe, feel free to drop us a line at training.request@pentair.com and be more than happy to take care of your needs there.